US 69 Missouri River Bridge design-build project that is also located in the Kansas City area. So due to the design-build nature of this project, in thinking about how we wanted to go about winning this project, we thought of using Midas for our substructure modeling because we wanted to get the most efficient substructure and then therefore on our design team, we were teamed with American Bridge, and our client was MoDOT. So I'll take you through a project overview, our design goals, the bridge layout and typical section, other bridge design considerations, and some bridge construction photos as it is today. And through that, I'll show you how we use Midas in an MDX Midas superstructure comparison, and also for our substructure design for our river piers. So the RFQ issued by MoDOT was issued on January 9th, and we were shortlisted. Working through the proposal phase, we used Midas in our iterations, and it really helped to know that as we iterated our geometry to get the most economical design, that as we were changing properties and geometry, that the cross sections were being updated reliably, and this cross section and quickly as well. So we did win this project in July, and construction started pretty soon after. And our project goals included the schedule. The bridge needed to be open no later than December of 2016. Also, the cost of the project, we needed to deliver the most practical and economical project to win the project. Also, we had to provide a durable bridge that was low maintenance and would provide at least a century of service. Our contractor had to ensure that during construction that they would have an exceptionally safe work environment. So as we were turning in our proposal, we were graded on our method of handling traffic and the Missouri River Bridge design and the contractor's safety plan. And just that was half of the points. And the most important set of points was the cost. And Midas really helped us get the most efficient structure so that we did win this project with all of the points. So our design goal in trying to come up with the most economical structure is we wanted to reduce earthwork, minimize bridge lengths, and have a constructible project. So we looked at different alignment alternates, and we wanted to maintain the same alignment that the existing bridges were on. And this is what we proposed for the project. So we had a lot of stakeholders on this project that required a lot of coordination, especially with the levee districts and the railroad as far as bridge design. So for further details into our design goals, we chose to maintain our traffic on the existing plat purchase bridge, and we removed the existing Fairfax bridge and placed our alignment along along that original alignment. So to reduce the bridge length, we closed Harvester Road and were able to bridge length on the Kansas side. Then on the Missouri side, we were required to reroute the Argosy Parkway that feeds to the Argosy Casino. And when we rerouted it, we used an existing bridge overpass and only needed to construct one bridge for that reroute. Once we rerouted Argosy Parkway, we were able to place a lot of fill in this region up to the levee to reduce bridge length at this location. And as you can see, this is the fill placement at Invent 10 location, and the existing plat purchase bridge adjacent to this fill is very close. And the fill is placed as close as we can to the levee. So it is very close to the existing substructure. In some places we had a temporary wall to hold back the fill to continue to maintain traffic on the existing plat purchase bridge. So as far as design, we had to consider a settlement analysis for that fill effect on the existing plat purchase bridge as we were maintaining traffic. So our geotech came up with uniform displacement or uniform settlement and differential settlement criteria that could be possible for the existing bridge. We did use MDX for the superstructure settlement analysis, but we did use Midas to look into the settlement on the substructure. So to ensure that we weren't reaching a maximum design settlement that our existing bridge couldn't handle, we came up with a settlement monitoring plan, and that included having the contractor come out and survey points that were placed on the bridge every day as the fill was placed. So this is what the fill is today. It's done being constructed, and luckily we did not see the maximum amount of settlement that we predicted. As far as the new bridge design, I'll take you through the span layout and talk about Invent 10, the superstructure typical section, the substructure typical vents, some bridge construction photos, and some other considerations. So we talked about how there's the existing bridges, in green, the Fairfax Bridge and the Platte Purchase Bridge. And to construct our new bridge, we had to remove the Fairfax Bridge, and the blue is our new bridge on that alignment. So at Invent 1, this is where Harvester Road was closed, and we were able to construct an MSE wall. The first span spans over the railroad, and Invent 2 is placed at the backside of the levee. And note that Vent 2 is very short, and that plays into our need to model in Midas. So our second span spans to our third vent, which is our first river pier. So our three main river piers are vents 3, 4, and 5. And what I wanted to note is that vents 1 through 5 hold a continuous plate girder unit, and then from vents 5 through Invent 10, that is a continuous pre-stress girder unit. So what we had to consider for bents 3 through 5, since they're river piers, is that there would be stream bed degradation and also scour and vessel collision forces, and I'll talk about that more later. So from bents 6 through 9 are overbank piers, and they carry the pre-stressed NU78 girders in this region, and bent 10 is placed at the backside of the levee. Now, as far as the levee is concerned, we were required to not encroach too far on the toe of the levee for bent 9, so we did skew that bent, and then we also skewed in bent 10 as well. This is where all that fill was placed, so for the existing plat purchase bridge, there's still three more spans past this point. So a little bit more about indent 10 that's just a little interesting for our project dealing with the levee is that the levee considers that there is a clay cap in their levee structure where that prevents seepage of water during a flood event to the dry side. Now, if you penetrate that clay cap with a steel pile, you can cause a seepage path. And according to the levee district, if we encased that steel pile in concrete, we would meet the seepage requirements. So to construct indent 10, we constructed the MSE wall with pile spacer. We allowed that settlement to occur. We pre-bored the pile hole with the polymer slurry so that earth would not fall into that hole and we could keep that hole open. We drove the pile to rock. Then we placed concrete in the pre-bore hole and removed the slurry. Then we filled the pile spacer with sand. Now for our superstructure, looking more in depth at our two units, our first unit is our steel plate girders, and the max web depth is 12 feet. Our superstructure carries 2 lanes in each direction and a shared use path. Our second unit is our 8 NU78 pre-stressed girders. And so in Midas, we modeled the first unit, the composite plate girder. Our design was an MDX, but we wanted a comparison in Midas. So when we put together that model, we used Midas's composite plate girders, and then to connect the plate girders for the beam element, or for the deck element stiffness, we used beam elements. And then also modeled every cross frame. So in looking at our results for a comparison between Midas and MDX, for our total factored moments for an exterior girder, which our interior girders, we had similar results, so I'll only focus on our exterior girder. Our factored moments were pretty comparable, but we wanted to look further into what the differences were. So we looked at our dead load moments, and those were very comparable. There was almost no difference. And the difference that we saw was live load moments. So MDX had more live load moments, and we tried to figure out why they would be different. Now, keep in mind that this is our first superstructure comparison between MDX and Midas. Also keep in mind that we had two designers. One did the MDX model and one did the Midas model. So in that coordination that occurred between two engineers, we feel that maybe not everything was completely updated due to our design build process. And so it might not have been 100% the same structural detail. Now, we do have another experience with another bridge where we did an MDX and Midas comparison, and one engineer did both the Midas and MDX model. And he came up with the exact same live load forces between Midas and MDX, and he did take the time to really see the differences in how live load was being modeled in both programs. So I would say that if we had enough time on this project, we probably could have gotten those live loads to be the same as well. So one more thing we looked at with our Midas and MDX comparison is dead load deflections. And in our 420-foot span, we did see the largest difference to be a coupling. Now, keep in mind, if you look at the other spans, that they are very comparable, but it is the main 420-foot span that has some differences. Another thing that we will continue to consider when we're doing our Midas and MDX comparisons in the future is that maybe there's something about having such a long span, a 420-foot span, that might be causing the difference as well. So, because on our other bridge, it had, or on the other project that we have this comparison experience, those were shorter spans. So maybe the span length also had something to do with it. So for our typical vents, we have two column vents, and the columns are 9-foot diameter. They're supported by drilled shafts, and there is a strut that connects them to help with vessel collision forces. So in coming up with our Midas models for our substructure design, we had to consider 4 different load combination and scour effect cases. First, we had an extreme event full barge load combination case where only degradation was considered for scour. For an extreme event empty barge load combination, we had to consider degradation in half of the 100-year scour. For strength and service cases, we considered degradation in the full 500-year scour. And then we had to do a stability check that is an extreme event case, and that is considering scour to bedrock. For our river piers, the extreme event full barge load combination cases controlled our design. So that's what I'll continue to talk about. So in coming up with our Midas model, our global model, to help us design our substructure for the vents that are supporting our Unit 1 substructure, or our Unit 2 superstructure, we we wanted to be able to consider the stiffness of the superstructure and the adjacent vents when it came to vessel collision forces. So we used the similar superstructure that we had that I showed you before. The only difference is that we did not use composite plate girders, but we used just a plate girder and plate elements to model our deck. We found that that was, when it came to lateral forces, that gave a better representation as to the stiffness for our lateral force analysis. So when we, and then we also considered nonlinear soil springs to help dissipate forces and reduce moments in our substructure. So as far as the actual vessel collision forces, first we had to consider a transverse vessel collision. And as you can see, those forces are mainly in the impacted vent, but there's also forces being resisted by the adjacent substructure vents. Then we also had to consider a longitudinal vessel collision force. And you can see that there's significant moments in the adjacent vents. So this really helped reduce the forces in the impacted vent. This longitudinal vessel collision case is what controlled our river vents, so I'll continue to talk about that a little more up close. With those moments, you can see that the nonlinear soil springs dissipated those moments over the length of the drill shaft. And if you look at our shear, you can see that above the impacted area, there is shear going up to the superstructure and then down through adjacent vents. We also had torsional springs in our model, and you can see how the torsion was reduced through the drill shaft length. So this is different than what an RC Pier model would give you, because RC Pier does not have soil springs, and also it doesn't have the stiffness of the superstructure and adjacent vents. So in this way, we knew that Midas was going to give us the most economical structure. More specifics on our nonlinear soil and rock springs that we input for our vents, for our drilled shafts. We used the integral bridge option in Midas and used pile springs for our soil springs. So Midas does only allow soil information to be input in this module, and so when it came to our rock springs, we did calculate our rock springs in the spreadsheet form, and then input them into Midas for point support springs. So kind of what you've seen is that graphically Midas is great at seeing what you're inputting in the program, and also seeing results graphically. And as far as their table, it's very easy to manipulate geometry and these soil or these rock springs in the model just by copy and pasting from Excel to the program, and then when it comes to results, extracting those results into a spreadsheet. So a little more detail, and what we had to consider as far as our analysis using nonlinear springs is that for nonlinear springs, you have to have all of the force of a load combination acting on a soil spring to get a reliable result from the soil springs. So if you only consider the load combination itself, it only takes each load case and its effect on the soil spring. And so if you only do that, the soil spring is stiffer than what it really should be. So to get all of the forces acting on the soil springs at the same time, we using load combinations and imported our load combinations to load cases, which you can see in the static load case. As we were doing this, I talked about, we had to have at least 4 models to model our substructure as far as different load cases and scour effects. But when it came to this process, we realized that the file sizes grew very large very quickly for each load combination that we were turning into load cases. So we did have to have multiple models because we would exceed the file size. So, which wasn't a problem. It's just we kind of hoped to only have 4 models, but because our geometry is so large and we had so many forces that we were reaching file size limits, and we had to go to multiple models for certain design cases. Another thing we found wasn't as far as analysis is we wanted to get p-delta effects on our substructure, but the way that Midas runs p-delta effects with nonlinear soil springs is it turns those nonlinear soil springs into linear springs. So if you're trying to do a p-delta analysis, you're not going to get the right nonlinear effects. And so how we kind of worked around that to be able to use nonlinear effects in our analysis is that we came up with an equivalent model that we could use for a p-delta analysis that did not have any nonlinear effects in it. So we ran the p-delta analysis and came up with a factor that we applied to all our forces outside of the program. And once we had that factor, then we went back to our nonlinear model and we used that throughout the project. Yeah, and I want to note that this is not something that only Midas can, so it's not a very specific program issue. I don't think any program out there can do this type of analysis of considering p-delta effects with nonlinear soil springs. So right now, until that someone does come up with that, this is kind of the process that we go through to get reliable results. And so once we got all of our forces into spreadsheets, we sorted them and found our worst cases and did the design off of those forces and in our own spreadsheets outside of Midas. So as far as constructing this bridge, we first had to demolition the Fairfax Bridge to make room for our for our new bridge. And in this process, when demolition occurred, they had to remove each piece of the existing steel braces from the navigational channel within 24 hours of the explosion. So they used a barge and they moved each piece to land and disassembled it there. So I'll kind of take you through the project as it is now. So from indent 1 on the Kansas side through the project to indent 10. In this photo, you see indent 1 under construction. Here you see indent 2 being constructed at the backside of the levee. Vent 3 drill shafts are being constructed, and both of these vents were designed using the Midas analysis and forces extracted from the model. So here's more in-depth a picture of the drilling process for vent 3 drilled shafts. And here's vent 3 fully constructed. And vent 2 to vent 1 has the superstructure placed on it. And there was a lot of coordination with the railroad as far as closures. They'd have a day of closure, and they'd be able to place several plate girder segments at a time, and so they were able to fully coordinate with that and get the first span placed. So a little bit closer on vent 2, you can see how short that is and how important it is to model that in Midas to get the forces, because it is so short, which means it's very stiff compared to our taller piers, and therefore attracts a lot of force. Here are our overbank piers that have been constructed, and vent 5 drilled shafts that are under construction. So looking back on the project, with the overbank piers, pre-stressed girders have been placed, and the drilled shaft on vent 5 has been constructed, and they've started drilled shafts on vent 4. Once vent 4 is complete, they're able to place all of the superstructure and finish this bridge. So here's more of the overbank piers and the pre-stressed girders that were placed. The deck is being formed, as well as the diaphragms at the piers. So here's vent 9 at the toe of the levee, and vent 10 has been constructed here, and this is also where all the fill is placed, and so the final span has been placed. So to kind of sum up the Midas advantages that we utilized on this project, being able to update the geometry during our design build iterations was very much a plus, and knowing that it was reliably calculated and it's very easy to manipulate the geometry in Midas. As far as getting results, Midas had great graphics to see how forces were being distributed through the substructure and superstructure, and the results tables were very helpful for extracting forces for design. Being able to use composite beams is also a great great option for modeling in Midas, which we did with our MDX and Midas comparison on our superstructure. And in the plate elements that we used in the substructure analysis, that we used for the deck elements to get the right stiffness for our superstructure, was very helpful. For substructure analysis for our global model, we were able to use the superstructure and adjacent vent stiffnesses to get the most economical substructure for our project. So, and then being able to utilize the nonlinear and torsional soil springs helped as well. And being able to do a nonlinear analysis was a great option. So some of our lessons learned were that for our substructure design, we would, for a bridge this size and with a lot of different load combinations, we would need many design files because we reached file size limits. And again, that's not an issue. It's just knowing that there is a limit on those file sizes, and that could possibly crash your model if you're trying it to produce too much data within the file. And then knowing that we have to do separate analysis if we want our P delta effects for our substructure, and that we had to consider nonlinear effects separately. And again, I don't think any software out there can handle these two together. But as I told you, that we found a way around this modeling issue. So with that, I'd like to thank Midas for letting me talk about our project. And if there's any questions, you're always welcome to email me at rehankhouse@garverusa.com. And you guys have been submitting questions to James, so I'll turn it over to James to see those, to discuss your questions. Hey, James.
Hi, Rachel. Thank you so much for that.
You're welcome.
Okay, so selected a few questions to go over with you, Rachel, and thank you for doing this with us. And
Sure.
The purpose of going over the questions in a limited basis is since we have limited time. So the first question is with regards to the fixed bearings and the intermediate piers.
Okay.
First, why are there fixed bearings in the middle of the three piers over the 800-foot continuous span? And your elevation view of the continuous plate girder on spans 1 to 5 showed that piers 3 and 4 were both fixed bearings. Why is that? Were there special thermal considerations that resulted from this?
Okay, so to kind of answer both of those questions, we did actually want Vent 2 to be an expansion pier. There were a few reasons why we ended up making Vent 2, 3, and 4 expansion, or 2, 3, and 4 fixed piers, and that had to do with the amount of force that was on Vent 2 made it so that friction was not overcome for normal forces. And so to even consider the friction force was more force on Vent 2 than if we just made it fixed. And once we also had Vent 2 fixed, it did help control movement of Vents 3 and 4 since they're very tall piers. and so let's see, were there special thermal considerations that resulted from this? So as far as thermal considerations, that was definitely modeled in Midas. So it was considered with those 3 vents being fixed.
All right, we'll move to the next question. Did you have to compact the sand inside the casing around the H-pile?
Oh, that would be a contractor's question and a geotech question. I'm sorry, I can't answer that for you. If you send that to me in an email, I'd be happy to get an answer for you.
Oh, yeah, we'll be collaborating on some of the remaining questions with you, Rachel. So attendees who are listening in and who submitted those questions, don't worry, we'll get to you. And the next question is, for the differing moments and deflections, what differences are there in the respective program's assumptions? Do they use the same theory for design?
So they do use the same theory. One thing we do know about the 2 programs as far as live load, how that's modeled, is how the trucks float in Midas when you place the lanes versus how MDX allows the trucks to float. There are differences that, so kind of our second round in this comparison, that is what that one engineer really looked into and was able to better match the live load moments. As far as stiffnesses, I really do think that what we saw on this particular project, that the differences did come from the fact that there were 2 different designers and the fast-pacedness of our design build project, that when we were doing the Midas model, that designer was going off of criteria that was an older version of what the MDX model was, the final design for the MDX model. So in trying to get back to the same comparison, we had to go backwards in our MDX model to get that. Our time constraints, I am not sure if it did get to the same geometry. If that.
Thank you. So for the next question, our technical support team actually already put together some answers, but the questions were, what caused the difference between Midas and MDX software? Is it because that one of them is simplified in the superstructure modeling or the structural analysis? And then the next question was, how was MDX model done, grid or plate and beam system? And the attendees can see the answers that are there, you as well, Rachel. Is there anything that you want to add as far as elaborating on some of these questions?
Okay, well, I know on the second question we did do a grid analysis on MDX. Let's see the first one. Yeah, and I would agree with your answers. Yeah, it is something that we will continue to look at in our future projects, the differences between Midas and MDX, and kind of once we get more comfortable in Midas and more trusting in Midas, then we could possibly see using Midas as our design and MDX as a check.